So I would like for you to look at this example and try it on your own. Pause the video and then come back to it to see if you got it right. So the question says the shaded boxes in the figures below represent a sequence. If figure 1 represents the first term, A1, and this pattern continues, so that's A2 and that's A3, how many shaded blocks will be in figure 35? So now, I don't know about you, but on a test, I would not have time to draw another 32 boxes following this pattern. So we should look at a relationship between the numbers. So let's count the number of shaded boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. 12. So now when we look at figure 2, well, let's see how it changes from figure 1. Well, if we actually just look at the inside here, this is figure 1. And what did they add to it? Just a row on the outside. So in that row, we have an additional 1, 2, 3, 4 shaded boxes. So this would be 12 plus 4, which is 16 boxes. So let's see if that pattern continues. Do we have the term before it? We do. And then we have the additional 1, 2, 3, 4 boxes. So this would be 16 plus 4 is 20. So what do we take from this? Well, is this arithmetic or geometric? It's arithmetic. And it has a common difference of 4 because we are adding 4 to each term. So we have our initial, we have our common difference, and we have which term we're trying to find. So we now can plug it into the formula a sub n equals a plus 1 plus n minus 1 d. So what is my n value? That's 35. That's the term I'm looking for. A value's initial is 12, right? Plus n is 35 minus 1, and my common difference is adding a 4 to each. Now, when I type that into my calculator, I get that figure 35 should have 148 shaded boxes. Okay? So that's how we can apply the same thing to visual patterns as well. So now we've talked a lot about arithmetic sequences. What about geometric sequences? Well, of course, there is an explicit formula for geometric sequence as well. And it follows this pattern. So we have a sub n is the term we're looking for. A sub 1 is the initial. R is our common ratio. And n is the term number. So now if we look at this formula, it should look kind of familiar to our exponential formula, right? A, b to the x, right? A being our initial value, b being our value we're multiplying constantly, and x being the number of periods. The only difference is that we're subtracting 1 because the first term is no longer associated with 0, but instead it's associated with the first term. There is no term 0. So how does this look like as a recursive versus explicit? So recursive, remember, always has an initial term, which in this case is 100, and the building term. So how do we get from this to this, this to this? Well, 100 to 50 would be divided by 2. We know we represent divided by 2 as multiply by 1/2. So does that pattern follow? 50 to 25 is multiplying by 1/2. 25 to 12.5 is multiplying by 1/2. So that means our common ratio is 1/2. So when I go to my recursive, I have my initial, and then I have my common ratio times the term before it. So how does this look like as an explicit? Okay, a sub n is the term. Now we don't have a specific one, so we can leave it. A sub 1 is my initial, so that's my 100. R is my common ratio, n minus 1. Okay, and that is an exponential function if you were to graph it. So that's the relationship between 6-2 and 6-1. So let's take a look at some more problems. So how do I find the 8th term? Well, we know anytime they ask you for a specific term, you can use your explicit formula. Okay, so what is my explicit formula? A sub n is equal to my initial term times my common ratio to the n minus 1. So how do I get from here to here? From -3 to 6, I multiply by a -2. 6 to -12, I multiply by a -2. So my common ratio is -2. So let's plug it in. What term am I looking for? 8. What's my initial term? -3. What's my common ratio? -2. My n value is 8 minus 1. So now I can plug this into my calculator, and I should get a sub 8 is equal to 384. Okay, when you plug this whole thing into your calculator, please make sure that the exponent only goes to this parentheses. All right, so, and make sure the negative is inside the parentheses, because if it's not, and it's just to the 2, you're going to get a different answer. Or you have the possibility of getting a different answer. Okay, so let's see how this works with word problems. So, suppose a balloon is filled with 5,000 centimeters cubed of helium. It then loses 1/4 of its helium each day. How much helium will be left in the balloon at the start of the 10th day? Well, we know that if it loses 1/4, right, we're not losing a constant value. So this is going to be geometric. So now we have to figure out what we are multiplying by. Well, anytime we had a loss, right, we would always take 1 and subtract that loss. So in this case, I'm going to take 1 and subtract 1/4. This is going to be my decay rate. Like, how am I shrinking? So my R is going to be 3/4. And that should make sense, because if I'm losing 1/4 of my air, I have 3/4 left. Okay, so let's fill in the rest. So a sub n, since this is geometric, is equal to a sub 1 times r to the n minus 1. So I'm looking for the 10th day. My initial value is 5,000. My common ratio is 3/4, because I'm losing. N is 10 minus 1. Now again, you can plug this into your calculator, right? And you should get approximately, let's type this in, 5,000 times 3/4 to the 9th power. 375.4. Okay, so you get 375.4 cubic centimeters left in the balloon on day 10. So it's going to be significantly deflated. Let's take a look at one last question, and you're done for videos. So, when a ball bounces, the heights of consecutive bounces form a geometric sequence. So what's happening here is I'm dropping a ball, it bounces, but it never reaches that maximum height again. It always gets smaller and smaller and smaller. So we're saying that this is geometric because it's going to be shrinking by the same amount. The height of the first bounce is 121 centimeters. The height of the third bounce is 64 centimeters. What will be the height of the fifth bounce? So, boom, boom. What's the height of that fifth bounce right there? Okay, so we know it is geometric. So we do know that we can use a sub n is equal to a1 times r to the n minus 1 if we need to. Okay, do we have any of this information? Well, we do have the height of the first bounce is 121. And we do have the height of the third bounce is 64. And we do have that we're looking for n equal to 5. But what we don't have is our r value. Okay, well, how do we find the r value? Well, if I'm given any 2, right, I can plug this information in to solve for my r value. So this would be 121. My r value is what we're solving for. My n is 3 minus 1. Okay, so it still looks kind of funny, and that's because A3 has a value. So really, I should be plugging in that value to replace it. And 3 minus 1 is 2. Okay, so now this is just a regular quadratic. I can divide by 121 to get my exponent alone. 64 over 121. And because it's just a square, I can take the square root of both sides. And I get 8 over 11. Okay, so my R value can either be positive 8 over 11 or negative 8 over 11. But because we are bouncing and we're in the real world context, we want positive only. Okay, so my R value is equal to 8 over 10. So that being said, I now can plug in A5 into the equation, 121, with my, I wrote that down, growth factor of 8 over 11 raised to the 5 minus 1 power. You plug that in, and we're rounding to the nearest centimeters, so we get A5 is equal to 34 centimeters, okay?